Chances are you've got one of these sitting on your desk or maybe tucked away in your bag right now. It's the humble power brick, and it feels like just a simple, solid block, right? But inside, there's some really clever engineering happening. So today, let's kind of metaphorically crack one open and see what's going on.
I mean, have you ever really thought about it? How does this little box take all that raw, high-voltage power, we're talking 120, even 240 volts, from your wall outlet, and somehow tame it into the safe, low-voltage DC that your laptop or phone actually needs? It's a fundamental challenge in all of modern electronics. And the answer? Well, it lies in a component that does a whole lot more than you might think.
And the hero of our story is the transformer. Now, you'd probably think its only job is to step voltage up or down. And yeah, it does that. But in these power converters, it's doing so much more. There are actually 3 absolutely critical reasons we just can't live without it.
Yep, 3. Not 1, not 2, but 3. And each one is totally essential for making our gadgets safe, efficient, and versatile. Okay, so first up, and this is the big one, safety. The transformer gives us something called galvanic isolation. Just think of it as a physical air gap. The high-voltage wiring from the wall never actually touches the low-voltage wiring going to your device. That gap is what protects you and your expensive laptop from any dangerous power surges. It's huge. Second, scaling. The transformer's turns ratio gives designers this amazing tool to make these huge voltage drops really efficiently. And third is flexibility. With just a few extra windings, a single transformer can create multiple different outputs, like the plus 12 and plus 5 volts your computer needs, all from one single converter.
So now that we know why the transformer is so important, let's actually see its magic in action. We're going to start with a really basic circuit and then watch what happens when we add a transformer. This is where the design possibilities just explode.
So our starting point is this little guy, a non-isolated buck-boost converter. It's a real workhorse in power electronics. It can step voltage up, it can step it down, but it does have its limits.
So before we add our transformer, the output voltage is all controlled by this thing called the duty cycle, which is pretty much just how long a switch stays on versus off. But look what happens when we add the transformer. Suddenly, we get this incredibly powerful new lever to pull, the turns ratio. This gives an engineer a whole new degree of freedom, a whole new level of control over that output voltage.
And just like that, by adding that one component, we've unlocked a whole suite of new features. Way better voltage scaling, that critical safety isolation we talked about, more flexibility in our circuit design. We can even flip the output from negative to positive. It's a real game changer.
This brings us to our first major design, the flyback converter. And it is built on an absolutely brilliant engineering idea, taking something that's normally seen as a flaw, a problem, and turning it into the star of the show.
Okay, here's the secret sauce. Every real-world transformer has this tiny bit of, you could call it magnetic memory. The technical term is magnetizing inductance. Now, in most designs, this is a pain, something engineers try to minimize. But the flyback converter does the exact opposite. It intentionally uses this magnetic memory to store and then transfer all the energy.
Professor David Perrault from MIT has a great way of putting it. He says the transformer in a flyback isn't really a normal transformer at all. It's much better to think of it as an energy-storing inductor that just happens to have a second winding wrapped around it. The way it works is this simple two-step dance. Just think of it like filling and then dumping a bucket of energy. First, the switch closes, and the primary winding fills the transformer's magnetic core up with energy. Then, the switch opens, and all that stored energy gets dumped out through the secondary winding to power your device. Fill, dump, over and over.
Okay, let's make this real. Imagine you need to convert 100 volts down to 10. Without a transformer, your components need to handle both high voltage and high current at the same time. That's kind of like trying to find a world-class weightlifter who can also run a marathon. It's possible, but it's really tough and expensive. But with a flyback, you can use that turns ratio to trade one for the other. Now you just need a component that's good at high voltage and a different one that's good at high current. And those are much easier to find.
So that's the flyback. Now let's look at another super clever design, the forward converter. It starts with the very same idea. Let's add a transformer to a basic circuit, but it uses a different starting point, and that leads to a totally different result.
See, the forward converter is, at its heart, just an isolated version of the classic buck converter, which is a circuit designed purely to step voltage down. And this different family tree means it operates in a completely different way.
So, unlike the flyback with its fill and dump bucket approach, the forward converter is much more like a direct pipe. When its switch is on, energy flows continuously from the input, straight through the transformer, and right to the output. There's no real energy storage happening in the transformer itself. It's just a direct conduit.
Now this direct pipe approach sounds great, right? And for higher power applications, it's actually very efficient. But, and this is a big but, there is a serious catch, and it has everything to do with that exact same property the flyback turned into a hero.
And here it is. This is the crucial difference. In the flyback, that magnetizing inductance was the design. It was the hero of the story. But in the forward converter, we want a perfect ideal transformer, a perfect energy pipe. So that very same physical property, magnetizing inductance, becomes the villain. It's a parasitic effect that stores a little bit of unwanted energy every single time the switch turns on.
So what do you do with that leftover energy? You can't just ignore it. If you don't get rid of it every cycle, it builds up and up and up until, poof, the whole converter fails. It's like a ticking time bomb inside your circuit.
This is famously known in power electronics as the core reset problem. The designer absolutely must add extra circuitry for one specific job, to provide a path to safely remove that stored energy and reset the transformer's magnetic field back to zero before the next cycle begins.
And of course, that extra reset circuit comes at a price. In a simple buck converter, the main switch only has to handle the input voltage. But in a forward converter, that reset mechanism means the very same switch now has to withstand twice the input voltage. And that is a massive penalty for an engineer to pay.
So what we have here is a classic engineering trade-off. On one hand, you have the flyback. It's simple, it's clever, it turns a bug into a feature. But because it stores all the energy, it can be a little bulkier. It's like carrying that bucket. On the other hand, you have the forward. It's more efficient, especially at higher power, like a direct pipe. But it's way more complex and needs those extra parts just to keep it from self-destructing.
So, what's inside your power brick? Well, it could be either one. There is no single best design here. The choice between a flyback and a forward converter really comes down to the specific application. It's this constant balancing act between cost, size, efficiency, and just how much power you need to deliver.
And that leaves us with one last question to chew on. Just throwing away that reset energy every cycle seems pretty wasteful. So how do clever engineers actually solve that core reset problem without just turning that energy into heat? And what other amazing circuit designs has this challenge inspired over the years? Well, that's a great story for another explainer.